Well, dear students, let's do some question. So, read carefully this question, what is given here. Identify which of the following plot for fixed amount. So, if it is given fixed amount, means N is constant, right? Of an ideal gas at constant temperature, means T is constant. So N and T are constant. So you have four variables. So if N and T are constant, then definitely there is a relation between P and B. So that simply implies Boyle's law, right? So answer, as you know, if N and T are constant, then these two variables are related like this. K, N and T are constant. This relation is called Boyle's law. Boyle's law. Now apply. Will be linear. So P versus V. So if you see in case of A, P versus V, it is not linear. As we know, P is inversely proportional to V, so it is non-linear. B part, P versus 1 by V, so definitely P versus 1 by V, this is linear. And if you see the slope, so slope in this case, the slope is equal to slope P versus 1 by V. So you can write P is equal to K by V, and intercept is 0. So slope here you will get slope intercept 0. So P is equal to, you can write K into 1 by V plus 0. So this is Y is equal to M into X plus C. So C is equal to 0. So slope in this case, slope is equal to K, right? Now C part, PV versus P. So if you take a plot, PV is equal to K. So if you have PV versus P, so this is also I mean linear or straight line, and this time slope is equal to 0, right? Slope is equal to 0. And this D, 1 by P versus V. D, 1 by P versus V. So 1 by P is equal to 1 by K into V, right? So this is another equation. 1, 2, 3, and 4. So 1 by P versus V. So this time slope is equal to right? So in case of B, C, and D, you will have slope and linear plot between the given variables. Plot between the given variables, right? Now, see, this is homework for you people. A diver at the depth of 45 meters exhales a air bubble of air that is 1 centimeter in radius. Assuming N and T constant, find the radius of the bubble and it breaks the surface. Means at the surface of water, you have to find and use the data when it is required, the standard data, what you are, having the values. Now see, this is another homework. This is a nitrogen gas taken here. The volume of this part of the container is 1.103 liter. Pressure is 710 torr. Volume of this connecting tube is negligible, and this is an empty container of V liters. After opening the valve, gas is homogeneously distributed in the whole system, and this time the pressure is 583.1 and the volume of this is this. Find the volume of this container. So simply you can apply the Boyle's law, right? Now come to this Charles law. Charles law is relation between V and T. This is the relation between volume and temperature. I am not writing here small t or capital T because we have two different units for temperature, and okay, linear relation, directly proportional relation is there, but not exactly directly proportional to. So volume and temperature I am writing in English. Slowly we will narrow down this. So Charles' law is the relation between volume of a gas V and T at constant P and N. So this time pressure and number of moles, means quantity is constant. This time we try to find out the relation between volume and temperature. So at constant we can write, we have two statements for Charles law, right? So first statement, and after I will write the second statement. So first statement is at constant pressure, the volume of fixed amount of gas is a linear function of its temperature, right? See here, I have not written here, specified here temperature at degree Celsius scale or Kelvin scale. So first I am taking the temperature in degree Celsius scale. So if you take temperature in degree Celsius scale, then this relation is like this: V is equal to V naught plus V naught alpha into T. This is the linear function of its temperature, right? This is the relation where V naught is what? V naught is the volume of gas at 0 degree Celsius, right? And alpha is coefficient of thermal expansion, right? Thermal expansion. One more thing that it is found experimentally that this alpha is constant for every gas. Means it is not dependent on the nature of the gas. So it is constant for every gas, right? So this is, but if gas behaves ideally, not if the behavior is not ideal, then this is not equal for all the gases. So alpha is the coefficient of thermal expansion. And what is T here? T is the temperature in degree Celsius scale. See, small t in the beginning, I have already told you that small t is for degree Celsius. This is standard. This is standard, right? So temperature at degree Celsius scale. And V is the volume of gas at T degree Celsius, right? So hopefully all the terms I have explained here. So V is the volume of gas at T degree Celsius. V naught is the zero at 0 degree Celsius, and alpha is the coefficient of thermal expansion, and T is the temperature in degree Celsius scale. Let's see one graph between V and T, how this volume varies with temperature in degree Celsius scale. Now see, I have taken two samples here, sample A and sample B at 0 degree Celsius. For sample A, the volume is 1 liters, and it is cooled. This is 0 degree Celsius. Now this side temperature will down. On cooling, the volume shrinks, and finally, if we extrapolate this graph, not necessarily do the experiment, means do the cooling at this. So on extrapolating this gas, this line, this plot when intersect at that point, that is known as absolute zero, and it is minus 273.15 Kelvin, or you can write here 0 Kelvin, right? Absolute zero, right? This is the 0 Kelvin, 0 Kelvin, right? So this is what uh, 0 degree Celsius, and here this is 0 Kelvin. Okay, minus 273.15 degrees Celsius is equal to 0 Kelvin, and I think experimentally we cannot achieve this temperature, and this is not that means unachievable temperature. So see, that's why this extrapolation is we are doing here. Now we can write certain facts. This is the sample B, which has under same pressure, means pressure of sample A, pressure P of sample A, sample of gas A is equal to P of sample B. Means pressure for both A and B are same, and samples are different. So obviously, if pressure is same, temperature is same, so if they have different volumes, so definitely they have different number of moles. But in the given sample, number of moles are constant, and temperature is pressure is also constant. So that's why these two graphs were given. It is not possible that pressure is same, temperature is same, right, and number of moles are same, and you have different what volume. It is not possible. So at this point, pressure of sample A and pressure of sample B is same, means and temperature is 0 degrees Celsius means temperature is also same. So if they have different volume, then definitely they have different number of moles. It is not possible that T is same, P is same, and N is same, and volume have different value. This is not it. This is impossible, right? So definitely both the samples have different number of moles. Okay, no problem. For one gas, if you see for one line, your Charles law is applicable, no problem. And for other sample, that's why I have clearly written here, A and B are not two. Same sample. They are the different sample. That's why I have written here. Pressure of sample A is equal to the pressure of sample B. What facts we can write from this graph, that when you cool sample A and sample B, the rate, right? The rate of this cooling, the rate of decrease in volume, you can say, in the sample B is more, right? Slope, you can compare. So you can write here that on cooling, sample B shrinks faster than sample A. First point. Second point, you can write. Percent change in the volume. If you see the percent change, then the percent change will always be equal for both the samples. So percent change per degree decrease in temperature per degree decrease in temperature is same for both the samples. Right? So this is the representation of what variation of volume with temperature at which scale? Degree Celsius scale. This is not Kelvin scale. This is not at Kelvin scale, right? And you know, at Kelvin scale, when it starts from 0, and I am telling you, and it is proved that no low temperature than this is possible, or it is in fact non-achievable temperature. So means temperature at Kelvin scale, there is no question of negative temperature at Kelvin scale. All these values are positive. So basically, when you simplify this above equation, what I have written here, then you will get the relation between V and absolute temperature, right? Okay, now see, this value of alpha is determined, experimentally, alpha is equal to 1 by 273.15, right? Degree Celsius inverse. This is found experimentally. Initially, this value was used to 65, but slowly this will rectify, and finally this value is accepted experimentally. So if you see the first equation at at the temperature T1, so at temperature T1, let the volume is V1 of a gas sample. So V naught plus V naught alpha T1. This is equation 3, where V1 is the volume of gas at temperature T1. Let the same sample is taken at temperature T2 and the volume is V2. So this is equal to V naught plus V naught alpha T2. Right? Equation 4. Everybody is clear here? I think there is no doubt. Okay, now you can simplify this equation 3. You can write here V1 is equal to V naught 273.15 plus T1 by 273.15. What I have did here, I have put this value alpha here and taken common this V naught. So this equation 5. Simply you can write V2 is equal to V naught 273.15 plus T2 divided by 273.15. This is equation 6. So you can divide equation 5 by equation 6. So V1 by V2 is equal to, you can write 273.15 plus T1 divided by 273.15 plus T2. And all of you are knowing that this temperature is a degree Celsius scale. So if you add this degree Celsius scale into this 273.15, so this becomes T1 Kelvin by this is T2 Kelvin. So basically you can write V1 by V2 or T1. V1 by T1 is equal to V2 by T2. Right? So this is the general statement of Charles' law, or V by T is equal to K, constant, and the value of this constant depends on P and N. Right? So this is the most general form of Charles' law. Now you can write here that the volume of a fixed quantity of gas is directly proportional to the temperature at Kelvin scale. Don't write volume of a fixed amount of gas at constant pressure is directly proportional to temperature. Don't write directly proportional to temperature. When you write directly proportional to temperature, then you have to write at Kelvin scale. Otherwise, you can use this statement. At constant pressure, the volume of fixed amount of gas is a linear function of its temperature. Or you can define this as well. If you take T is equal to 0 degree 1 degree change, alpha is equal to 1 by 273. So V is equal to V naught plus V naught by 273.15. So you can write volume of a gas increases by a factor of 1 by 273.15 per degree rise in temperature of its volume at 0 degree Celsius. So these statements you can use, but you cannot use that volume is directly proportional to temperature. No, not like that. You have to use volume of a gas directly proportional to temperature at Kelvin scale, at constant P and N. right? So this you can write. And now if you plot V versus T, so V versus T, so this will start from this origin, right? P and N constant. So suppose that we have different points. So here V1 T1, so here V2 T2, right? P and N are constant. Clear to everybody? And this time no need to write here at Kelvin scale. Capital T means Kelvin scale, right? Similarly, if you draw a plot, what is slope here? Slope V is equal to what? K into T. So slope is equal to what? K. Slope is equal to K. And here, if you see, if you take V by T versus T or V, so you will get this type of plot, and P and N are constant, and this time slope is equal to 0, right? So this is the different plots and Charles law. So Charles law tells about the relation between volume and temperature at constant P and N. And one term all of you have gone through here, that is alpha. This is called coefficient of thermal expansion, right? And this is this will be constant for every gas if your gas behaves ideally. If your gas not behaves ideally, then it is not what parallel. This is not constant for all the gases, right? So hopefully all of you clear in the in this law, Charles law. Okay. Now see this isothermal compressibility. See, this is a new term for you people, but not as much as new, because now you have relation between pressure and volume at constant temperature. So isothermal means temperature is constant. Compressibility means gases are compressible. What is the meaning of compressibility? If you apply the pressure, volume changes significantly. So if you talk about solid and liquid, so solid and liquid are less compressible, much less compressible compared to the gas. So basically gases are compressible or maximum compressible. Maximum compressible. Right? Compared to the solid and liquid. We cannot say that solid and liquid are non-compressible or not compressible at all. We cannot say this, because if you apply high pressure, then definitely there is some change in volume. So the compressibility is, whenever this word is come to you, definitely you will visualize this like if we change in the pressure, then how this volume changes. So gases are maximum compressible among solid, liquid and gases. Among solid, liquid and gases. So among solid, liquid and gases, gases are the maximum compressible. How this is given? This is written in a small k. This is known as kappa. Kappa, right? So kappa is equal to small k kappa is equal to 1 by V and del V by del P, change in volume per unit change in pressure, and this whole divided by total volume means this is the fractional change. Basically, this is the fractional, you can say fractional differential change in volume, right? This you can define like this. This is a mathematical term, no relation with the chemistry, at constant N and T. So this is the expression for this isothermal compressibility. How it is defined? You can define this, that fractional, why it is called fractional? Because this total volume is divided to this term is divided by total volume. So if you take this whole term as a numerator here, so you can say that change in volume per unit change in temperature, pressure, right? So fractional differential change, fractional differential change in volume due to change in pressure, due to change in pressure at constant N and T. So this is the isothermal compressibility. How to find this isothermal compressibility value of this, right? If you want to evaluate this value of this, so kappa N and T are constant. So if you want to evaluate this value, so how to evaluate this? You can use Charles' law, right? Sorry, Boyle's law. Because in Boyle's law, N and T are constant. So you can write here PV is equal to K, N into T are constant. So this is the Boyle's law. So by using Boyle's law, you can evaluate the value of this kappa, right? You can use this direct definition kappa, and now you can evaluate. So this is not kappa, this is K, basically constant, right? Okay. So you can differentiate this del V by del P, as we have already differentiated, but that time we have evaluated del P by del V. This time I am evaluating del V by del P. So del V by del P at constant T and N is equal to, we can write here minus or we can del K by P by del P at whole N and T, right? And this is equal to minus K by P square, minus K by P square, and K is equal to PV, you can write here, so minus K is equal to PV, P cancel, V by P, right? V by P, minus V by P. So this is equation A, this is equation B, right? So now you can use this kappa. We have evaluated this delta V, del V by del T. Del V by del T is equal to minus V by P. We can put here and find the value of kappa. So kappa and T is equal to minus 1 by V into V by P, minus V by P, minus V by P. So V cancel, so this is equal to 1 by P. So basically this isothermal compressibility is nothing but it is reciprocal of what? Pressure. So more you apply the pressure, if this pressure is more, right, the isothermal compressibility is less. This is the reciprocal to the pressure. So sometimes this type of questions, say mathematical questions, may be asked, right? But the meaning is change, fractional differential change in volume due to change in pressure at constant N and T, right? Similarly, if you see the relation between V and T, then volume is expanding on temperature. So this type of expression you can find out. This is compressibility, isothermal compressibility, that is the cubic expansion or isobaric thermal expandivity, right? That also you can calculate. So these are the different terminologies. Sometimes it may be asked. Now see isobaric thermal expansivity or cubic expansion coefficient or coefficient of thermal expansion alpha, as you have already gone through in Charles law. So this alpha is given by this expression. Alpha is equal to 1 by V into del V by del T, del V by del T at constant P and N. So again you can make the definition, this same definition, fractional differential change in volume with change in temperature. So what is this coefficient of thermal expansion, alpha, or isobaric thermal expansivity or cubic expansion coefficient? Fraction of differential change in volume by change in temperature due to change in temperature at constant P and N, right? Now, how to evaluate this del V by del T? You can use Charles law, that V by T is equal to constant V by T is equal to K, constant at P and N are constant. So you can differentiate this del V by del T if you want. So del V by del T at constant P and N is equal to del of KT by del T at constant P and N, right? And this equal to, you can write what, K and K is equal to, from here you can write K is equal to V by T. So this is equation 2. So you can evaluate alpha is equal to 1 by V into V by T. So this is equal to 1 by T at what? Kelvin scale, right? So alpha is basically 1 by T. And it is taken constant for every gas, and it is equal to 1 by 273.15, right? So this alpha is equal to 1 by 273.15. This is constant, right? So this is isothermal, or isobaric thermal expansivity, or coefficient of thermal expansion, and its evaluation in terms of known variables, temperature and pressure. So first one is the compressibility factor, because there is inverse relation between P and V, and here expansivity factor, because T and V are directly proportional. Okay, good. Now see, we have two relations, P and V and V and T. Now we have a relation between P and T, similar relation. This is not new law, you can say. Pressure is directly proportional to temperature if N and V are constant, and this is called Amental's law of pressure. Amental's law of pressure. Although we are not recognizing this as a separate law, because this we can find out this with the help of what? Boyle's law, basically, right? So you can write here P1 by T1 is equal to P2 by T2. So that's why I'm not giving much focus on this. I'm just writing the formula. One more law, fourth, that is one more combination is left, V and N. So V is directly proportional to N if T and P are constant, and all of you are knowing this. This is called Avogadro's law. Avogadro's law, right? Or V is equal to K into N. Or you can write V1 by N1 is equal to V2 by N2. Sometimes this, question you may get directly on this these formulas, but be careful that what variables are given constant there, right? So this is also one law, Avogadro's law, and this is Amental's law of pressure. This is not new. This is the same as the Boyle's and Charles law. All the derivatives, whatsoever we have taken there, compressibility and expansivity, everything is similar. So ratio of, you can say, this is the ratio of alpha by kappa, right? See, if you take this del P by del T, this is at constant V and N, so this is equal to K. If you take the differential of this equation, P is equal to K into T. If you take the derivative of this, you will find this, and this is equal to alpha by kappa, right? This is K. This is K and this is kappa. So if you want, you can derive this expression. So that's why I'm telling this is not any new law. That is the rearrangement of the variables. That's it, right? So in this way, we can make the relation between, direct relation between all these variables, and all these mathematical laws are said to be gas laws, in which the most important are Boyle's and Charles' law. And these are the, supporting mathematical relation, you can say, and you can find the relation as well. But numericals you may get from any one of this mathematical relation, right? Now see, there is one question. They see the pressure of air in an automobile tire at 15 degrees Celsius was P atm, right? After the tire warmed to 35 degrees Celsius from driving, what was the new pressure, right? So see, in this question, which law you have to going to apply. See, can we assume the volume of tire is constant? Yes, we can assume, because there is no much change in the volume of tire. It is a rigid structure. So V is constant for tire. And n is also constant. So if v and n are constant, so can we make the relation between what p and t? So p1 by t1 is equal to p2 by t2. This we can use. So we are going to use this equation. First, what is p1? So P1 is equal to what is given? P atm. So if you use P1 is equal to P atm, your answer will be wrong. You know why? See, when you take P1 is equal to P atm, so this is the, see, pressure of air in an automobile tire was P atm. So is this a gauge pressure, or this is what you can say absolute pressure? This is the point. So if this type of question is given, then you have to always consider whatsoever the pressure it is given, that is a gauge pressure, right? So this is a gauge pressure, and in this formula you have to use the absolute pressure, right? So P atm, and I have already told you the absolute pressure is always this include 1 atm, right? So this whenever you take this gauge pressure as a final pressure, your answer will be wrong. So the initial pressure is P plus 1. This is equal to P plus 1 atm, right? And P2 we have to find out. T1 is equal to 15 plus 273, right? So we can take 0.15, we can ignore 538, 718, 288 Kelvin, and T2 is equal to 35 plus 273. This is equal to 538, 0308 Kelvin, right? So now we can find out P1, P plus 1 or 1 plus P divided by T1 288 is equal to P2 by this 308, right? So P2 is equal to this 308 by 288 into P plus 1. So this is 308 divided by 288, 1.06. So 1.06 into P plus 180, right? So this is absolute pressure. Absolute pressure, right? And if you want to make this gauge pressure, find out the gauge pressure, then you have to, subtract that 180, then you will get the what gauge pressure. So every time you have to clear in your mind that when you are taking the tire pressure, so gauge pressure and absolute pressure both are different, right? So here I have taken absolute pressure and calculated what absolute pressure. Okay, and if you want, you can if the examiner wants, then you can calculate what gauge pressure, right?